Okay, so that was the pyrolysis part, and now moving to the biomass gasification. So, gasification is another way of having a higher yield of hydrogen without looking into multiple reactors like we have seen in the pyrolysis, where we do pyrolysis in one reactor and the hydrogen yield or hydrogen enhancement in the separate reactor. So, we have already seen the understood the gasification, pyrolysis and the combustion part. So, typically gasification, as the name suggests, conversion of biomass solid fuel to a gaseous fuel. Gaseous fuel easy, handy to use, to store, to transport, unlike the biomass which is a little inconvenient for multiple use. So, that is the simple thing why the gasification is done. So, now gasification is a substoichiometry combustion of a fuel. So, typically less amount of oxygen that we are supplying. Yeah, so gasification, it involves pyrolysis, oxidation and the reduction process, and we will see what exactly happens in the next slide. So, typically biomass, we know it contains the CHNO, and then when we heat it, what we get is it undergoes pyrolysis and we get the volatiles. Volatiles is nothing but your combination of higher hydrocarbon, as we have seen in the earlier pyrolysis process. Also it gives you carbon monoxide, hydrogen, this is CO2 etc. and all, but also it gives the charcoal, around 20 to 30% of charcoal by weight, and volatile is around 70 to 80% by weight. So, these two, now in combustion process we burn all, as we have seen in the example of the matchstick, both are burned, but here in gasification what we do is we only allow the volatiles to undergo combustion, and what we get is H2O and CO2. Now the role comes of the charcoal. Charcoal acts as a reducing agent which reduces H2O and CO2 to carbon monoxide and the hydrogen, and these two are fuel. So, these two are the good fuel, though carbon monoxide is a poisonous gas, but we know that it is a very good fuel, and also carbon monoxide is one of the substrate or the feedstock to give us more hydrogen through water gas shift reaction that we will see in the subsequent slides. So, this together is called the synthetic gas, or in short syngas. So, this is what we get in the gasification process, a very simple process, and if we understand, as we discussed in the last slide, that is a substoichiometry process. So, now if we look into this graph, this x axis is the equivalence ratio, and when we say equivalence ratio of 1 means it gives enough oxygen for complete combustion, and that is what we mean by stoichiometry. So, this is the stoichiometry point where we have the enough oxygen, and if here it is less oxygen and beyond this point we have more or excess oxygen. So, when we are talking about the pyrolysis, it happens without the presence of oxygen. So, 0 oxygen is there, no oxygen or absence of oxygen, or just in the inert like nitrogen gas environment or something. But gasification happens when we are supplying around 20 to 40% of the required oxygen amount, and here we get finally the carbon monoxide and the hydrogen as a product. And as we have seen in this particular slide, this is not a single step but a multiple step where the pyrolysis, combustion and reduction, all the three processes happen together in a single reactor. So, again to reiterate physically how it happens, we first thing is the process the drying, where we heat the biomass and remove the moisture. So, typically gasification process 20 to 30% of the moisture is allowed, because moisture removal is a very highly energy intensive process. So, overall temperature gets reduced if we are putting very high amount of moisture, and typically many of the green biomass will have 40 to 50% of moisture, and it will be difficult to process here. So, first we need to dry it, and then this is happening below 200 degrees centigrade. So, typically more than 200 degrees centigrade, the organic molecules they start undergoing thermal decomposition or what we call as pyrolysis. So, below 200 degrees you will not see any of these molecules will undergo any molecular change or compound level, nothing new will come out. But more than 200 degrees we will get, and what we get here is charcoal that we saw 20 to 30% by weight, and the tar, and this tar is 70 to 80%, and this tar is nothing but the volatile. So, this is nothing but the volatile only. It has a, in literature you will find a different terminology for that. So, now when it undergoes combustion, because we are passing oxygen and air. So, now the question comes, as we discussed, we will allow only the volatiles to burn, but how to do it in a single reactor if you want, how to achieve it in a single reactor with a selective combustion. But the beauty of the process is that chemistry itself take care of it. What happens if we supply oxygen and air, but this tarry gas, this is gas, and then it reacts with oxygen which is also in the gas phase. Gas-gas reaction is very fast, but this is solid. So, this is charcoal is present in a solid form. So, this fuel is solid. Solid gas reaction is very slow. So, this is very slow and this is very fast. Not only few times, but more than 100 times faster than what is the solid gas reaction of carbon with oxygen. So, what happens is most of the oxygen because the statistics and probability will favor the gas phase reaction, and 99.9% of the oxygen will be consumed only by these volatiles. So, volatiles will consume most of the oxygen, and this charcoal will just remain and go into the reduction zone. So, what it raises its temperature because it is present in the flame, because this tarry gas it now not only undergoes combustion or oxidation, but also releases lot of heat. So, here CO2 H2O plus heat is produced, and this heat drives our reduction reaction because this is endothermic. This is processes or this reaction is endothermic. So, here we have C plus H2O and C plus CO2, it gives CO plus H2, and this gives us 2 mole of CO. So, this is endothermic in nature, both the reactions, but this hot environment that has been created by the combustion of the volatiles sustain this reaction with the charcoal, which is now do not have any access to oxygen, but it has access to CO2 and H2O, and it is happy to react, and then it releases our H2 and CO2 as the product. So, that is the overall process of biomass gasification, and if we look into the reaction, then combustion. So, typically some part of the carbon will burn, but yeah, very minor negligible amount, and then most of the oxygen will be consumed by volatiles when it reacts with oxygen, and also it produces heat. And then the water gas reaction, this C plus H2O and Bordeaux reaction, these two are major producer of our fuel gas, that is the hydrogen and the carbon monoxide. Another reaction that I was talking about is the water shift reaction, where carbon monoxide also reacts with H2O. If there is enough H2O present, or if H2O is present in the system, it will not only attack carbon, but also it will react with carbon monoxide, and carbon monoxide and H2O is now, this is a gas phase reaction. Gas phase reaction, again it is favored more compared to this solid gas reaction. So, here this also gives you hydrogen, extra hydrogen, and this is one of the thing that when we want to enhance the hydrogen production, we can use this H2O to enhance more and more hydrogen into it. And then we have a methane production, and this is also slightly sort of exothermic, but this is also very the occurrence is quite low compared to these 3 reactions. So, these 3 reactions that goes in the reduction zone are prominent, and this is less prominent, and this volatile oxidation is more prominent, and this is less prominent. So, this is the overall chemistry of the gasification process. And now when we look into the technology, just to give a brief history of this gasification, especially the biomass gasification process, it is a very interesting history. It was the Second World War was going on, and the US, UK and the Allied forces, they found that the blocking the supply of the petroleum may hamper the German forces, because Europe as such, Germany was almost holding the complete Europe, but Europe does not have much of a petroleum reserve. They have lot of coal, but they do not have enough petroleum reserves in the Europe. So, and it was dependent on either Gulf or the other countries in Africa for supply of the petroleum oil. So, that was cut down, and then German forces or the Hitler, he was a bit taken back, but then there was one scientist called Fischer-Tropsch. Typically it is called the FT synthesis. So, Fischer and Tropsch came up with the synthesis, FT synthesis process, where carbon monoxide plus H2, it undergoes a catalytic conversion process where it gives you higher hydrocarbon. This higher hydrocarbon can be petrol, diesel substitute or kerosene, or even up to wax. You can even create a wax. So, it creates a sort of, it is a polymerization process where your carbon and hydrogen is here and oxygen is left out. So, oxygen is not part of this product, it is left out. The polymerization of carbon and hydrogen chain gives you higher hydrocarbons, which can be equivalent in the properties to petrol and diesel, which was required by the military. So, and Europe has a lot of coal reserve, even the Germany itself had a huge coal reserve, which was used to undergo gasification process similar to what is biomass gasification. We will come to it after this module, the coal gasification. So, this carbon monoxide and hydrogen was diverted here, but this process was costly. So, the military application was only given the access to the liquid fuel, and the normal population, civilian population were not allowed to use petrol or diesel. So, it was completely banned. The sale of petrol and diesel in the civilian areas were completely banned throughout the Europe. So, then the researchers came up with the biomass gasification and the engine technology. So, what they do is, rather than looking for coal or something, can we, because this process of FT synthesis is costly, not the gasification process, and biomass is also available. So, rather than coal gasification, they designed such reactors which were biomass gasifiers and which was producing gas. So, it was giving you carbon monoxide, hydrogen and the methane, and this was going into the ICE engine. So, they developed the process, the technology which can fuel the conventional petrol or the diesel engine. So, diesel engine has to be converted to spark in a spark ignition mode, because this fuel does not ignite by compression ignition is not possible for this, but it easily ignites with the help of a spark plug, and especially this hydrogen is a very good fuel in terms of its ignition properties. Hydrogen plays a very important role. So, you can see that even in the tractor, even in a two-wheeler. So, it was lot of things are produced. There was a company in Poland which has retrofitted such gasification system like this, and other in the trucks and buses and all, they have retrofitted of more than 1 million vehicles. So, you can just imagine how popular it was during the World War II era. But once the World War was done away, the petroleum supply in the Europe was very good, very smooth supply was there, and then the completely shifted back to the fossil fuel, and this technology slowly died down. But again it picked up during the 80s when there was again oil crisis. But that time it was not for the running the vehicles, but for power production. But yeah, so that was a very nice short history of this gasification, which I thought that it will be interesting to share here. Now again coming back to the gasification process. So as we have discussed, again we will try to recap: drying, pyrolysis, combustion and reduction. Drying happens typically in the temperature range of 20 to 150, pyrolysis more than 200 degrees, and then oxidation zone goes very high temperature 1000, 1100, 1200 degrees, and this then whatever the leftover charcoal, and because those reactions carbon with H2O and carbon with CO2, they are endothermic, the temperature reduces to around 800 degrees or so, and this oxidation zone is supplying heat for this reduction process, as well as it is supplying heat for this pyrolysis process, as well as it is supplying heat for the drying process. So all the heat supplied is from this oxidation zone. As you can see here is, this is the oxidation zone in this downdraft reactor. So this reactor is the downdraft reactor here, and this through the radiation, through the radiative heat transfer, it supplies the heat to the pyrolysis zone and the drying zone, and then air is drawn from here, and all the oxidation process happens and the hot gases passes through this reduction zone. So upper side the radiative heat transfer, and in the reduction zone mostly the convective heat, because it is the hot gases which is carrying the heat with it, comes to the charcoal and supplies a bulk amount of heat, because it requires lot of heat to convert the solid carbon into gases. It is a slow process, so a temperature has to be remained high. Pyrolysis can happen at 200, 300, it is fine with it. So this is the typically process, and then from the bottom we draw the gases. So typically updraft gasifier will have a different configuration. So these two are for termed as packed bed reactor, packed bed, and they take the bigger size of the biomass particle, and these two are the fluidized and the entrained flow, which takes the small size particle, and this takes the bigger size particle. So we will not go into the detail, but yeah, chemistry is important to understand from this part. Now coming to our main point, we are looking for hydrogen. Okay, we have understood the gasification. I hope you have got the basic chemistry and overall reaction process in the reactor, how in a single reactor itself we are able to produce gas, and the basic chemistry also, but our intention is how to get the higher yield of hydrogen. So there is a limitation by the air gasification. So in the air gasification what we have is, we are just limited by around 60 grams of hydrogen in the biomass. Then typically only 35 to 40 grams is achieved, that is 35 to 40 grams of hydrogen per kg of biomass, that is only achievable. And another issue is this nitrogen which comes with the air, because air 77% by volume is nitrogen. In the gas also we get around 45% by volume of nitrogen only, and hydrogen is limited only around 20%. So then it becomes very costly or non-viable to separate it. Once is this small amount of hydrogen in the yield, as well as the low fraction. So the separation also becomes a little bit costly. So the process that can do away with this limitation is, first is using the oxygen to eliminate to increase the hydrogen volume fraction by eliminating this nitrogen. So if you remove this, automatically hydrogen fraction, volume fraction will go up, or approximately it will get double, but yeah, it will not increase the amount of or the mass of our hydrogen in the product gas, but that we can enhance by using steam as a gasification agent. So and we have seen with the reaction with carbon and carbon monoxide through water gas reaction and water gas shift reaction. So these two reaction, so again if we look into that, so these two reaction, so water gas reaction with carbon plus H2O, and the water shift reaction, that is carbon monoxide plus hydrogen. This gives us a high amount of or excess amount of hydrogen through it, and here we can get more than 100 grams of hydrogen by it. And this endothermic reaction, this is highly endothermic, and then this is the high adiabatic temperature causes operational issues. So, if we use these two alone, then we face problem, but if we combine these two through oxy-steam gasification, replacing nitrogen by steam, so oxygen fraction will still be low, it will not give us operational issues, and steam fraction, which participates mostly in the reaction in the reduction zone, will give us high amount of hydrogen by reacting with carbon and carbon monoxide. So, these two combined together give us a very good stable operation of the reactor gasification system with the high amount of yield of hydrogen. So, here again what is the role of steam here is, one is the steam reforming, then the water gas reaction and the water gas shift reaction. So, here we can see it is the steam which is giving us this hydrogen mostly. So, here hydrogen is coming from here, that we have seen in the pyrolysis process also, but here in the water gas shift reaction H2O is coming purely from steam, in water gas reaction also hydrogen is coming purely from the steam. So, typically biomass gasification, air gasification, which is limited by 35 to 40 grams, here we can enhance it, we have got around more than 100 grams of hydrogen per kg of the biomass, and that is almost 200% exa steam. And this is the beauty of the system, that we can use the carbon in the biomass to get the hydrogen. So, and this is one of the results from the publication, that as we increase the steam to biomass ratio. So, this is steam to biomass ratio, as we increase from 0.5 to 1 to 3, and when our hydrogen yield is also increasing. So, y axis is hydrogen yield is around 60-65 grams, it goes more than 100 grams at the equivalence ratio of around 2.7. So, that is the beauty of this system of the oxy-steam gasification. So, this is the result, as we increase the steam to biomass ratio, our hydrogen yield is increasing from around 66 grams to 104 grams. And typically the biomass gasification, biomass contains around 60 gram, and we are able to add 44 grams extra to get the 104 grams of hydrogen per kg of the biomass. So, with this slide I would like to end or summarize this particular module. So, here in the starting we have looked into the chemistry of the pyrolysis process. We are using the bio oil reacting with a steam in a catalytic reactor to get more hydrogen, and then move to the gasification process, where we try to understand the air gasification, the chemistry behind it, how in a single reactor, unlike the pyrolysis process where we have to go through two reactors, one for pyrolysis and one for pyrolysis bio oil catalytic conversion to more hydrogen. Here in the single reactor we are able to get in the gasification process pyrolysis, combustion of the volatiles, and then the reduction of the CO2 and H2O by carbon, that is the charcoal itself, and then when we use extra steam we can enhance the hydrogen production just like we did in the pyrolysis process, but in a single reactor. So, here we summarize the module for this pyrolysis and gasification part and the biomass part. In the next module we will discuss about the coal and the coal gasification and the hydrogen from the coal in the next module. Thank you.